All right, we are going to wrap up buffers in this lesson, and it will lead into our weak strong titrations later this week. So the first thing we want to just discuss briefly is buffer capacity. So the capacity of a buffer has to do with the strength of the buffer and really its ability to maintain the pH following the addition of a strong acid or a strong base to it. So capacity gets influenced by a couple of factors. The first big one is that the concentration, the greater the concentration of the buffer components, the greater the capacity. Okay, the more of that weak acid and weak base that you have, the more that's present there to react with that strong acid or a strong base. So for example, the 1 molar acetic acid with the 1 molar acetate ion has a greater buffer capacity than something, say, with a 0.1 molar of each of the acetic acid and the acetate ion. So again, the more you have present there of both the weak acid and weak base, okay, the greater it's going to be able to maintain that pH as you continue to add in a strong acid or a strong base. The other part is the more equivalent the concentration of the weak acid and weak base in the buffer, the greater the capacity. So you want to try to keep the ratio between the components close to 1-to-1 as you can. The less the ratio changes as the buffer operates, the smaller the pH change is going to be. If you start with a bigger ratio or bigger difference between them, it's just going to minimize the capacity of it and won't be able to maintain the pH as you add in a strong acid or a strong base. So you're looking for greater concentrations of the components, but also equivalent concentrations, if possible, between the buffer components. So another aspect of this is a buffer range. So basically, what's the pH range over which a buffer is effective and can continue to operate? So what we're going to see is usually this ratio that we use in our Henderson-Hasselbalch equation, you want the ratio to be no greater than 10 of the ratio, but also no less than 0.1. So what that really means is that unique buffers are going to have a usable range within a plus or minus 1 pH unit of the pKa. So in our acetic acid acetate ion buffer, the pKa of the acetic acid is 4.74. So that means our buffer range would be about between 3.74 and 5.74. So it would operate best between that range. One other little topic that I want to throw in here, not that it goes necessarily with range or capacity, but it's going to be important when we get into titrations, is just how when we compare the pH of the buffer solution to the pKa of that buffer solution, it gives us a little bit of information about the weak acid concentration versus the weak bases concentration. So this is just a little extra thing to put in here, and we'll come back to this when we do titrations. So what we're going to see is when the pH is equal to your pKa, that means the weak acid and weak bases concentrations are equal to each other. And that's referred to in a titration as your half equivalence point, which is going to be important. It allows us to use our pH in order to get our pKa. But also knowing what happens before or after that halfway equivalence point is also important. We can do that by looking at how the pH compares to the pKa of the weak acid. So if our pH is greater than our pKa, and think about this ratio up here, that means then that the concentration of your weak base is going to be greater than the concentration of your weak acid. If your pH is less than the pKa of the weak acid, then that tells us that, and I have to switch this around right here, that then means that our concentration of our weak acid is going to be greater than the concentration of the weak base. So it can kind of help you, especially if you're analyzing a diagram at a certain point along a titration curve, and we have a buffer region in our titration curve for a weak, strong titration. Knowing this relationship can kind of help you problem solve kind of what's going on in the solution, how do the components compare to each other. So we'll come back to that, but I just want you to get this in here next to this area of buffer capacity and buffer range. All right, the next part that we're going to go over is, well, how do people prepare a buffer? What are things that they have to take into consideration? So in this question, it says we need approximately 1 liter of a buffer solution who has a pH of 3.9, and we have access to a 0.4 molar HCOOH, or formic acid solution. That's our weak acid. So the first thing, now this one I'm telling you which one you're going to use. So that's just something to kind of keep in mind for this. Usually you might be given 3 or 4 options and you have to pick out which one you want. So say we didn't know that we only had the formic acid solution. What you want to do is you need the pKa to be close to your pH. So this said that we needed a buffer with a pH of 3.9. So we're going to say that our pKa, ideally, we want to be 3.9. So if we plug this in, we would have 10 raised to the negative 3.90, which would give us 1.3 times 10 to the negative 4. So if we had a couple of weak acids to pick from, we would want to pick one with its Ka closest to this number. So we would want to pick a weak acid with a Ka close to this. Okay, so for formic acid, it ends up having a fairly close one to this, which we could look up in the appendix of our textbook. So then we have to, the second step, once you pick which weak acid, weak base you're going to work with, we then are going to calculate the ratio of the buffer component concentrations. So the pH is our desired pH. So again, we're trying to create a buffer with a pH of 3.9. So this is our desired pH. Then we're going to plug in the pKa of formic acid, which you would be either given the pKa or the Ka, which I'm giving you here, is 3.74. And then we're going to solve for the ratio. I'm going to plug that part in here. Okay, so once you rearrange this, you would end up with 0.16 if we subtract 3.74 from each side. That. And then we would take each side and raise it to the exponent to the power of 10. So we would have our 10 raised to the 0.16 is equal to our ratio that we're interested in. Okay, which when you get to that 10 raised to the 0.16, you would get 1.4, which I'm going to write it as 1.4 over 1. Would be equal to my ratio. So what does that actually mean in terms of the calculation that we're going to do? All right, so what we're going to do here is say that for every 1 mole of our HCOOH, we will need 1.4 moles of our weak base. Okay, so that gives us a relationship between our weak acid and weak base. Then we want to determine our buffer concentration. So we want to find out, because we already know that we have from this question access to this 0.4 molar formic acid solution. So usually you're going to see most of the textbook practice questions having to do with, okay, well then how much of our salt that contains the conjugate of that weak acid, how much do we need to add? So in this case, and you'll see the practice examples similar, we want to find the grams of, and in this case I'm going to tell you we're going to use HCOONA in here. So using the information in the question, we want a 1 liter solution, so I'm going to start with volume there of my buffer. Now I know that, and this is my solution, I know that I have this 0.4 molar formic acid solution, so I'm going to go next with that for every 1 liter of my solution, I'm going to obtain or have in there 0.4 moles of HCOOH. Okay, then using the ratio that I have from my step above, I'm going to plug in that for every 1 mole of HCOOH, I'm going to need 1.4 moles of HCOO minus. And then from there I need to figure out, well, how many grams of my salt do I need? So I have my 1 mole of HCOO minus, and that's going to be present in, because of the 1 mole of it in the compound, I'm going to have 68.01 grams of HCOONA. Because don't forget, that's going to be a part of the mass of the solid that we're adding. And again, that's just the molar mass of the compound. So keeping to the 2 sig figs, I get 38 grams of HCOO minus Na. So that many grams would need to be added to 1 liter of a 0.4 molar formic acid solution. Okay, in order to get a buffer with this 3.90 value for its pH. Okay, now usually the buffer pH may vary slightly based on that. So then as you're testing the pH, you would add a little bit of a strong acid or strong base dropwise in order to get the buffer to that desired pH of 3.90. Okay, so as you want to practice this, I would say initially try out like maybe the first 1 or 2 and just how to find, how much of your salt you're going to have to add. So you just get comfortable with it. It's not a huge concept that I'm going to focus in on when we get to an assessment, but just a process that you should be aware of. There's also a couple of review questions towards the end of the practice, just finding the pH of a buffer based on the components using the Henderson-Hasselbalch. So I would definitely say make sure you go back and do 19.19 and then also this 19.27. Just what happens to the pH changes to the buffer. So again, do something like 19.3, maybe 19.3a, and then the bottom 2. I'll also post some extra practice and some other videos that you can watch as well.